Hello everyone, welcome to the afternoon session on the network adjustment in another exciting power hour. My name is Boris Kopyak. I'm the product manager for TBC. You probably heard my voice before if you've attended these. Today we have a special guest speaker, Richard Hassler. So Richard, I'll let you introduce yourself in a few sentences to the audience.
Hi everybody, welcome to Boris's Happy Hour. I'm Richard Hassler. I'm a market manager in Trimble in the geospatial division. I've been with Trimble for a number of years and have worked on adjustments and putting together the TGO and TBC adjustment routines. So I have some experience in this area, and hopefully I can explain the TBC workings well for you.
Yeah. Really happy to have you, Richard, today, as Richard also brings a ton of practical experience as a professional land surveyor in his life prior to Trimble. So really excited to hear more from his experiences on the adjustment. So today we're going to just kind of start with some network adjustment concepts, and then this is going to be one of the rare slides you're going to see in the session, as we typically try to focus more on the live software workflows, and we'll try to spend the majority of our time today in the software working through the network adjustment steps. So Richard is going to be taking us through the project settings in TBC. Then we're going to dive straight into the adjust network command and the workflows. We're going to be talking about the weighting and constrained versus unconstrained adjustments. We're going to be looking at elements of the network adjustment report that are more critical to us, and talk about adjusting, what happens when you're adjusting different data types, when you have a mix of different data in TBC, and then provide some summary along with some next steps for those that are new to Trimble Business Center. And we'll try to leave a 10-15 minutes towards the end of the hour for any questions that you might have. So please make sure to type in any questions in the chat window, and we'll try to get those answered as we go, and we'll also try to have some time again towards the end. So please start typing those questions in whenever you have one. So Richard, I'll let you take us away from here.
Okay. So I wanted to start the talk today with a quote from a land surveyor that I thought was pertinent to our discussion. Surveying is the science of determining errors and the art of minimizing them. I think that particularly applies to least squares adjustment, because there is a little bit of an art to getting through the process of doing an adjustment and knowing when to turn things on and off, and which pieces of information from the adjustment to look at different times of the process. So because we're so focused on errors in network adjustment, I wanted to start my discussion talking about those. We are really trying to provide estimates of how well we measured each of our observations to the adjustment engine, and then letting the engine compare how much it has to adjust our observations to what our error estimates say they should have been allowed to move. So that's a big part of the network adjustment process, and using least squares, and that's what we're going to be focusing a lot on today. The second thing I wanted to bring up at this point is that the least squares process, or least squares adjustments, have two different stages to them. The first stage is the minimally constrained or free adjustment, as it's called, and that is where you're focusing on the internal consistency of your network and how well all the observations fit with each other, and trying to remove any blunders that may have occurred in the field work or in any subsequent work you did in working with those vectors, and get rid of the blunders, get rid of all of the problems from the data, and make sure that your network fits together very well, and you have a very appropriate set of estimates for the errors for all of those observations. Once you achieve that, then you can move on to the second stage of the adjustment process. It's called the constrained adjustment, where you start fixing control values, whether they be control coordinates for points, any kind of elevations or heights that you may want to tie to, that are the control for your project. and pulling those in and looking at the results of using your observations or your network with those constraints, and going through all the steps to evaluate whether the control fits well with your data. So given that, I'm going to move on into the software and start to describe how you set up an adjustment and how you perform an adjustment in TBC, and some of the things you need to look for at different pieces or different places in the process. So I'm going to start off by looking at the project settings for each project. So we in this project, I have a set of GNSS vectors or GPS vectors. I think these are actually just GPS. From control points around our area, this happens to be near our office here in Colorado, there are some federal agency control points that can be used for horizontal control for this network, and the network has a lot of points in it that are right around our office area. So we have a mixture of horizontal control or 3D GNSS derived points, lat, longs, and heights, and we have a lot of points that have benchmark only or elevation only control quality coordinates. So the different icons you see represented on the screen here are indicators of which coordinates for those points have control quality values on them, if any. And the square box indicates a benchmark, and the triangle, for example, represents latitude and longitude or northing easting kind of coordinates that are control, and if it has a dot in the middle, then all three, northing easting and elevation, or lat, long, and height, are fixed. Okay, so going into project settings, you can see network adjustment area, and we'll look at the settings quickly for those. In the general tab of the network adjustment settings, there are a couple important controls. The first one, do you want to perform a vertical adjustment? If you're, for example, running total station network or observations, and you're just citing the back site for angle only and aren't concerned with doing the 3D measurements on your back sites, just looking at it from a 2D perspective for azimuth or for angle, you can turn off the vertical adjustment and adjust just the horizontal components of your observations and make that work. Maximum iterations, the network adjustment will, the engine will perform an adjustment after an adjustment after an adjustment and look at the different coordinates that were generated from one iteration to the next iteration and compare the amount of change that took place in the coordinates with each subsequent adjustment. We have a very, very, very small number in the software that is the threshold for that comparison. And if the coordinates are changing by a greater amount than that threshold, then it will perform another adjustment, and it won't stop until you meet that threshold criteria and the coordinates stop changing. That means you have a stable adjustment. You can set the maximal number of iterations that occur to get to that point in the tab here. Typically, it won't take very many iterations for an adjustment to converge. It depends on how bad your starting coordinates are, and a lot of factors could have an impact on that. But by default, we set that at 10. All right. The last option here is the mean angles. I can use for terrestrial data or total station data, I can use individual observations, each separate angle that I turn by itself as a separate observation, or I can use the mean turned angles that are generated from our field software as a single observation, even though you may have turned that angle 10 times in the field. You can use it as a single observation. And there is some benefit to doing that because you can also use the standard deviations of the values for the angles and the distances from that mean turned angle record as the error estimate for inside TBC, and provide some nice weighting capability for you. Okay, I'm going to just skip the covariance display and go to another section in the general or network adjustment area, and that's the transformations. For a GNSS adjustment, you are using coordinates that were derived from the GPS data or directly from the satellites as your starting coordinates essentially for the processing of these vectors. And then you process the vectors either using the engine in RTK or using a post-processing engine, whatever kind of vectors you have. It'll process those vectors and come up with coordinate values that are essentially tied to the satellite datum. When you go to start fixing coordinates for your points in the network, when you're doing your constrained adjustment, you can calculate rotations and tilts and scale factor for your network to fit with your control the best it can. So those are parameters that you can solve using the least squares adjustment. And that actually is better than trying to distort your network to fit the control when all you really needed to do was rotate it a little bit and scale it and make it fit very, very well. So you'll retain as much of the internal consistency of your network as possible while making it match the control values, and you'll get better fit for your final control or final coordinates for the unknown points by doing that. So we'll look at that a little bit later, but here is where you can control whether that takes place or not.
So Richard, from the practical point, does it even make sense to turn those to no, those GNSS scale rotation settings? I mean, would that kind of kill the whole point of the network adjustment?
No, not necessarily. I have, and it's hard to describe conditions that would be ideal for doing it, but I have seen networks that perform better, especially with the tilts that are calculated for the network in certain kinds of geometry, long linear kinds of surveys that run pure north-south and things like that, where it actually was better to let the observations take the adjustment than to try to perform one transformation for the whole thing. That's pretty rare. Most average data sets, kind of like the one I'm showing here, where you have well-placed control and a fairly decent geometry for the final network, where it's probably best just to leave those transformation parameters on.
Yeah, we have two questions that are coming in from the audience, Richard, and William and Andrew's question is kind of both related around site calibration and network adjustments. Is it true that one can perform site calibration or a network adjustment, but not both in the same TBC project?
That's correct. Cannot have both.
Okay.
Okay, go ahead, Boris.
Andrew's question was, when you do a network adjustment and include deflections, rotation, and scaling, does that create a local site? So maybe if you can just clarify kind of both.
Okay. So you'll see a set of parameters, transformation parameters for this network generated from the fixing your observations to the control. Later on, I'll show you a little bit of that. And that set of parameters is different in its general nature from the site calibration parameters you get in using RTK, because the site calibration parameters are more where you're matching a set of coordinates by rotating, scaling, and translating them to another set of coordinates. Here we're rotating and transforming a set of observations so that they match between the control coordinates, and they are fundamentally different and basically incompatible with one another in some way. So you will have to choose whether you want to have a calibration or a network adjustment in your project. You can do a network adjustment and get an adjusted set of coordinate values that you use in another project to use as the control for a calibration if you choose. But what the important thing to note is if you do calculate a set of transformation parameters from your network adjustment in TBC, it will be stored in the coordinate system definition. It doesn't make a local site, but it actually stores the parameters in your coordinate system definition, and those rotation scales and rotation scales and tilts will be applied to any other GNSS vectors you bring into the project, including RTK or any side shot vectors that you chose not to include in the adjustment. So that stuff will be rotated in and tilted in to match the adjusted coordinate system that you're in. So it basically fundamentally changes the coordinate system just like RTK parameters do.
Okay, so if you have a local site, or sorry, a site calibration performed in TBC and you're doing a network adjustment, you will see a message that the side calibration is going to be removed, or same if there is a network adjustment and you're performing side calibration, you get a message you want to clear the adjustment.
Exactly. So it will tell you that you can't have them both, and which do you want to do?
Okay.
So, all right. So I'll get a little bit more into the parameters. I'm glad we kind of conquered that now, because it make the discussion easier later when we actually start calculating those parameters. All right. So the next section I wanted to cover in this project settings are the default standard errors. This is a place where you can, and I'll show them to you, and then I'll go back to the screen I'm on right now. This is the place where you can hand enter in error estimates for your horizontal, for total station, for example, for your horizontal angle, vertical angle, slope distance, etc. And you can also enter in centering errors and height errors. Now, typically what you would put in here is, if you're going to choose to use the project settings as your source for the error estimates for your observations, then you would put in values that match probably the manufacturer's data sheet for the instrument that you use for your total station observations. That's a good starting point. As you gain more experience with network adjustment, you may find that you're constantly scaling those error estimates to a larger value or to a smaller value, just because, typically larger value, because of those errors were derived, those error estimates were derived in perfect operating conditions set up on pillars in a warehouse. So or out in a really nice field in perfect conditions. You're going to be operating in real-world conditions. You may see greater error typically in your sets of angles than that error estimate for the instrument would indicate. So you may wind up scaling these every time by roughly the same amount. You may choose to go in and just put that larger value in as your default standard errors to start with. Make the adjustment a little bit quicker. So that's one thing that I wanted to note. The other thing are the default centering, and by the way, okay, and default centering errors. You have the ability to put in an error estimate for how well you feel you can set up your instrument or your receiver over the point in your tribrac. How well is your tribrac calibrated, and how well can you eyeball and get that instrument right over the point? You want to put a realistic value in here for how well you feel you can do that on a regular basis. Typically, I would put in, and I'll show you for GNSS, I typically start at usually using an error in the height of an antenna of about 3 mils if I'm using a tripod and a tribrac and one of our height measuring rods, and an instrument centering area of something like 2 mils for a well-adjusted tribrac over the point. If I'm using a fixed height rod instead of a tripod for my setups for GNSS, I'll put in perhaps a slightly better, maybe 2 mils for my height of the antenna, or even 1 possibly, and then an instrument centering error that's larger because it's harder to get a fixed height rod right over the point than it is a optical tribrac. So those are some really important things to get right. You want to put in your best guess at what you think is right for your instrument centering error and your height of instrument. Okay? The second thing I wanted to point out here, or the last thing really, is that on the default standard errors main tab or main fields here, you see that you have the ability to use the project settings if you choose, or you can use the data from imported files. So source for standard error, for example, for total station, I may choose to use imported files for the standard errors for a lot of sets of MTAs or mean turn angles, whereas for the centering errors I may choose instead, and typically do, to put in my own centering error values. That's the way I typically work. From GNSS receiver, when you process the vectors, either in the post-processing inside TBC or in the instrument or in the receiver for real-time kinematic, you get a difference in position, a vector between your 2 points, but you also get error estimates for how well that vector processed. Those estimates are approximations in some respect, but they're pretty darn good educated guesses based on the constellation of satellites and the amount of data you collected and lots of different parameters in there inside the processor itself to calculate those error estimates. So I choose in GNSS almost exclusively to use the baseline processor for my source of standard errors for GNSS vectors. But you do have the ability to hand enter values if you feel like you want to experiment and put in values of your own for azimuth distance and delta height. And you can see that here for horizontal and vertical errors. Okay. So
just
I think
just to add on top of that, on the imported files, what we mean by imported files is that's basically coming directly from Trimble Access. So if you open a JXL or a DEC file in Notepad or some other Word editor, you will notice next to an observation there is a standard error. So that standard error is computed in Trimble Access, so it's pretty kind of a standard or safe to use this imported files for standard errors in case of total stations. In the case of centering errors, you may want to, as Richard pointed out, you may want to kind of have a little bit more control on your own over those, knowing the quality of your equipment or how much are the tripods and tribracks aging, and kind of as you do more of these, you might want to adjust these values over time.
So just as a note, the way the settings are right now is typically how I do my adjustments with imported files for total station standard errors, baseline processor for GNSS, and centering I put in my own values. Okay. So given that, I think we have those settings in the right place for us to continue on with an adjustment. So the next area I wanted to go to, once I'm ready for my adjustment, I can go to Survey Adjust Network and start to look at what's available here. Now, it's easier for me to run an adjustment and talk about this information rather than to do anything more. So I'll go right into adjusting the network as it stands right now. And by the way, we're doing the free adjustment right now, not the constraint. So we're doing the first part, trying to find blunders and trying to find errors and bad fitting vectors and that sort of thing. And I don't need to fix any coordinates right now or fix any constraints in order to perform this adjustment with this network. I have a choice. I can fix one of the horizontal coordinates if I choose to. It's not necessary at this point because internal constraints will be chosen for the network if I choose not to fix any. All right. So I'm going to run adjust.
So Richard, these points that we are seeing in the list, those are points that have some kind of a control coordinate value associated to them. But let's say we have also some side shots or multiple RTK shots on one point. Are you saying all of those points, these are in the these points in the list, as well as the points you will be adjusting in the network adjustment, they're all going to have equal weight on the adjustment in the unconstrained adjustment that you're running right now?
Yes, I'm not constraining anything. So basically what I'm telling the adjustment is go ahead and move all of my points. However you want to move them any way you want to. In order to make the observations all fit together into one consistent network. So I'm not holding anything to a specific value and telling it, make sure you don't change that particular coordinate value. I'll talk a little bit later about what the points in the list represent, or what the values in the list represent when I get to the constraint adjustment, but basically I'm just telling it, don't fix anything. No azimuths, no distances, no coordinates. Adjust the observations that you have. Okay? So I hope that answered your question, Boris.
Yes, thanks.
So I'm moving on to try to hit the adjust button, and I get an error message or a question that it's asking me. And it says, I still have a computation error in this network. Now, my advice is for you to try to do your best job of removing all of the computation errors in your network, any kind of inconsistencies that the comp engine sees before you even get to network adjustment, so that you don't have anything that is basically a blunder in your network that you're feeding into the adjustment engine. You may find additional blunders as you start to adjust, but try to remove the computation errors, and that will greatly reduce your data snooping problems that you have when you're doing your adjustment. Now in this particular case, if I say, no, I don't want to continue with the adjustment, I want to look at that blunder or that error that it's pointing out, or the comp engine problem. If you look at what I have for my comp engine, it's telling me that point B412 has a horizontal coordinate that's out of tolerance. So it's trying to compute the horizontal coordinate for B412 from any way that it can, and every way that it can, and then compare the coordinate values that it gets at the end for that final horizontal coordinate that the comp engine is trying to put on the point. So it's telling me I have a horizontal error. Well, if I look at the point 412, it's actually a benchmark point. And that point, original coordinate for the point was brought in from a data sheet from some agency's control website that had a precise or control quality elevation for the point. And I want to use that in my adjustment. The problem is that they didn't have a good quality horizontal coordinate for that point in that data sheet. The best that they could come up with was a scaled value from a map. So when I imported that data sheet, I read the software read that read in the coordinate, horizontal coordinate for the point that was nothing more than a scaled off a map coordinate, and now it's trying to compare that to coordinates I'm getting from this GNSS data, where the coordinates are much better, and it's seeing a disagreement for 22 meters. Well, I don't really care that it's finding an error in that map, in that mapping quality coordinate that I brought in. So I'm going to ignore this error, because ultimately I'm going to calculate a much better position, horizontal position for that point from this adjustment anyway. And I'm not going to fix the erroneous coordinates. So I'm going to let the comp engine yell at me, and then every time I adjust, because I understand why it's telling me I have a bad coordinate here.
So Richard, we have a question for Jay, who's asking, for your control network, do you typically use published NGS data, or do you take a 2-hour minimum reading and submit to Opus and then run network adjustment just on the control, then add additional observations to the network with the adjusted control?
Whatever you feel is right for your network. I mean, you in the end have to report the coordinates for this thing depending upon what you're going to use them for. If it's a project you're going to do some kind of construction work in this area, and you're doing a boundary survey of points in your project area that you want to use for later construction project, you're probably going to tie it to some kind of control that's a little bit more local, maybe not a national network, but some kind of a city or a county, or some kind of a published set of coordinates from a local agency rather than the federal agency. But the choice is entirely up to the surveyor what he wants to use for his final control values. If there are no government control points in the general vicinity of your project you'd like to tie to, you may have to, in the U.S., basically create your own by using an Opus adjustment, providing data to Opus and getting an adjustment of that. So that's a surveyor's call, basically. I can't really give too many rules of thumb other than do what you think is right for the control you need.
Yeah. Also,
okay.
is there a reason or a way to clear those warnings that you know you're not concerned with? And would you actually try to tamper with the flags by changing the quality of conflicting coordinate, or as you just did, would you just ignore it?
It depends on the situation. In this case, I could actually delete that data sheet and go in and create a coordinate value under B412 that's purely a vertical only coordinate, doesn't have any other coordinates on it, a vertical underneath the B412, and use that for my control later, or my constraint later, and that would get rid of that message. In this case, I can choose to ignore it, and it doesn't bother me that it's there. Choice is yours how you want to address that kind of stuff.
But if you leave that, as Ryan is suggesting here, if you leave that bad coordinate, horizontal coordinate value for point B412, won't that skew the adjustment?
It's not a control quality coordinate that it's yelling about. So okay. No, when I have my final adjusted values that are assigned to these points, they're going to rule over anything other than control quality in the network. So they'll be higher ranked than the survey quality, and it will put my adjusted value on the point. It may still throw a message in my point derivation report showing that that scaled mapping coordinate is bad, but that's not a problem for the final coordinate values that I'm going to output.
Okay.
Okay. So I got to give me just a second to get back to where I was. All right, so I ran an adjustment, or I'm going to run an adjustment, and it's going to throw that message. I don't care about that message in this case because I understand why it's telling me that. And now I can look at my adjustment results. So I'm going to just go straight to the adjustment report to look at it very quickly. And that because we're doing a minimally constrained adjustment right now, I can focus on two particular areas that are really the most important to look at right now at this time. One is the adjustment settings, just to verify that the numbers you put in for your centering errors make sense, or what you expected to see there, because you want to double check and make sure you get those centering errors right. All right. The second part is the adjustment statistics, where it's telling me what just took place. So it's telling me that it had to run this adjustment 2 times, and when it did the second adjustment, it found no changes in the coordinate values that required it to go and continue to adjust the network. Already the coordinate values had converged on such a small amount of change from one adjustment to the next that it didn't need to continue adjusting anymore. All right, so that's a good indicator that, you know, that's a pretty stable set of observations. The network reference factor is indicating to you how much adjustment each of these observations had to take in order to all fit together to minimize the square of some of the squares of the residuals, as the way it's described, compared to the error estimates that you got for put into the adjustment for these observations. Those error estimates came from the processor. It's telling me I had to move my observations 1.2 times larger than the error estimates for those observations in order to make them fit together. And additionally, it is applying a statistical test called the chi-square test, which is basically testing your assumption of how well you estimated your error compared to how much they had to adjust, how much they had to move to make the adjustment work. And it's telling me that it failed. The chi-square test failed. 1.22 reference factor is too large for this particular set of observations to have to change in order to make them fit. All right, so I'll get to that a little bit more.
What is a practical value that you go by in terms of this reference factor, and is there any meaning if this number is bigger or smaller than 1, or is it always larger than 1?
Yes. So if you have underestimated your errors, or you're more optimistic about how well those you made your measurements compared to how much they have to move to adjust properly to fit together, you're going to see a reference factor that's greater than 1. And by 1.22, it's telling me about 1.25 times larger error estimates are needed to make these really my statistics work out correctly. All right. If the number is less than 1, it means that maybe you put in too tight a value. I told it I could turn angles to 5 seconds, and really my observations aren't changing by more than 2 seconds. So if it's less than 1, that means that you've predicted too large an error for your observations. And as I get to scaling, I'll talk about a little bit about your second point, Boris. Okay. So right now, I failed my adjustment. I need to do something to make it past my adjustment. Because all of these vectors in this network adjustment come from one common source, this is in my way. How do I get that out of my way? Presentation stuff's getting in my way of trying to show you guys what I'm doing. So because all these vectors come from GNSS processing, they all are common data type. They all their error source comes from the common observation of satellites and the common source. All 3 components of those vectors, the azimuth, the delta height, and the distance, all have errors that derive from the processing of the raw GPS data or GNSS data. So I don't have a mixture of different observation types in this network, so I'm going to get one reference factor, and I'm going to basically scale all my errors up and down by 1 factor. If I have a terrestrial observations, I'm going to get different reference factors for each separate component of the observation. I can show you that in just a second. The azimuth, or the angles, the zenith angles, and the distances will each have their own reference factor. For GNSS, I get just one. So what's my best guess at how much I would need to scale my error estimates to make this network statistically pass? Well, the best guess is my reference factor, because it's an indicator by how much more, it's a good indicator for how much you need to scale your observations, to your error estimates, to make everything fit together. So I'm going to do that right now, and statistically it's going to improve things, but from a practical point of view, it's not really going to change a whole lot in this network. So, because it's all GNSS only. So I'm going to go into weighting, and this gives me the opportunity to apply a numerical value to my error estimates to make them bigger in this case, to make this thing statistically work. So I'm going to take that reference factor for my first adjustment, multiply my error estimates by it, and then look at the final output of my next adjustment and see if statistically that makes everything come together. And I'll hit adjust. I'll blow through that warning again and look at my results. When I look at my results now, what I see is that I've passed the chi-square test and my reference factor is exactly 1. Well, that doesn't surprise me because I only have one data type in this network. So applying that scalar worked perfectly, but I'm not done evaluating whether this is a good adjustment or not, because I haven't gone down to this other section that lets me look at how much adjustment each one of my observations took to fit together. So if I go to the adjusted GNSS observations section, I see all of my observations in this list. The observation values are listed here, and the amount of adjustment that each observation component had to take to make this network fit together is shown here in this residual section. So those residuals have units to them. I had to tweak this thing by this delta height by 4 centimeters in order to make it fit with the rest of my observations. I had to change my ellipsoid distance by 1 millimeter and so forth. So all of these residuals need to be reviewed, and as a way of making that task easier, we also calculate what's called the standardized residual. This is a dimensionless number that's used to allow you to compare these different kinds of quantities, the azimuth, delta height, and ellipsoid distance, together in one histogram or in one distribution to see how all of them fit together with each other, even though they have different units on the original observations or the original components. So additionally, we sort all of the vector components together by the largest standardized residual for any one of those components in this list. So this minus 5.896 is the worst standardized residual, or the biggest standardized residual, absolute value sense, in the entire list for any of the observations. So we can plot the standardized residuals in a plot, calculate the mean value for it, and then plot those standardized residuals and look at them, and in a perfect world they will basically be distributed in a normal way, or what's called a Gaussian distribution, or a bell curve, right? So we'll see this kind of bell curve around the mean, and the largest, in an absolute value sense, standardized residual will be farthest away from the mean. And that, if it's far enough away, it will actually be flagged as an outlier as an outlier statistically from the entire rest of the network. And the criterion that we use to evaluate whether statistically it's too far away from the mean is called the Tau Criterion. And that Tau Criterion is just exactly that. It's essentially a vertical line, some number of standard deviations away from the mean, that tell you anything that lies outside of this line, any value that's bigger than the Tau Criterion, should be rejected as a statistical outlier. That observation needs to be removed from the adjustment because it's not fitting properly with the rest of your observations. So in this case, I've actually have a network adjustment that's passed. You have to get your state basically to as close to passed as you can get before you make this evaluation of whether you want to throw things away. And I still have one observation that has a component that's not fitting properly with the rest of my adjustment. So I'm going to remove that vector, and I can explain a little bit why I feel justified. You basically have to justify keeping it in there. So maybe you have to set up underneath some power lines, and you have very noisy GNSS data, and the conditions are just terrible for GPS, but you need to set up there in order to get a vector that's critical to your network to allow it to be adjusted. You may, in some instances, decide, I'm going to live with that particular observation, even though I know it's kind of noisy, because I need it to get the adjustment done. But in most cases, you're going to just throw away observations one at a time. You may have 10 of them in there. You might have to find which one is really causing the bad fit in your network. But you're going to at least throw away one of your observations to see if you can make this thing fit together without giving you any flagged values here. All right, so in this case, the observation that was highlighted was this one. It's the vector between two of my points, which ultimately I'm going to fix as horizontal control points for this network, and I'm not really going to care much about the vertical values of those in the end. They're only being used to tie down the horizontal coordinates for this network. And that vector between those two is currently having a vertical problem. So I'm going to highlight that vector and go to the properties and disable that vector so it's no longer used in this adjustment because it's not fitting properly with my adjustment. When I do that, I want to clear out all my adjustment results and start over again, now with a network that shouldn't have any bad fitting lines in it. So it still might, and if it does, you might have to go through this whole process again until you get rid of any of the values that aren't fitting properly. Sometimes it might be the third one you remove that's causing all the problems, and you can put the other two back in and everything still fits together. So you got to pay attention to that process. So I'm clearing my adjustment out. I no longer have an adjustment in this project. I've removed that vector, and I've turned on only enabled vectors so I can see that it's no longer part of my adjustment process. So now if I hit adjust, I'm going to get results that reflect what the network does without that vector in it. And it still fails chi-square, but by a lesser amount than what I was seeing before. And that's just because the baseline processor error estimates are just a little bit optimistic. All right, so I'm going to go back in and look at my weighting strategy once again and weight my error estimates from the processor by my reference factor from the first adjustment and adjust one more time. And I'll say yes, and in this particular network, when I do that, I get, and most of the time with GNSS only networks, you're going to get it to pass your chi-square and your reference factor will converge very close to 1, typically. And then when I look at my adjusted GNSS observations, nothing is flagged now for removal. All of my remaining observations fit together well enough that they fit in the distribution properly, and I can continue with my adjustment. All right, at this point, I'm done my minimally constrained adjustment. I feel confident that my network fits together well enough and I can continue on. That means that I will no longer change the weighting for any of my error estimates. I'm assuming they're done properly now, and the next step is for me to go to the constrained adjustment and start to fix my values. Okay, so with that said, I hope I haven't missed any key points yet.
So Richard, can you explain us a little bit more again where those coordinate values are coming from, and why are some of the checkboxes grayed out and some are not?
That's where I was going to go right now, Boris. So Boris wants me to explain this list. This list is created from all of the coordinates in this project that have control quality, all of the points that have control quality coordinates on them. Some of these points are benchmarks. For example, this point B412. And I'll try to go to Project Explorer and show you.
It's probably going to be up in the points node.
Oh, sorry, in the points node. Show you under B412, I've imported, first of all, lots of observations that go to that point from DAT files or from different files. There actually is even in this project some text file that was brought in that's the data sheet that indicates, as I said before, that that's a benchmark point. It has a control quality coordinate on the elevation and lesser quality coordinate on the other components. and there's even an office entered on this one. So it's a little bit of an aberrant case. It has so many different options here, but those coordinates that you see in this list that are available to you to fix in the adjustment come from the different kinds of control quality records you have in your project. Some can come right from the field files, the JXL. You can put things as reference coordinates and get control quality, and others are just coming from data sheets that you're downloading from the internet, and others could come from spreadsheets that you import and list them all as control quality. So B412 is a benchmark. The only control quality coordinate on it is an elevation, and that's the only thing I'm allowed to fix on that point. Point PLTC and TMGO are both federal agency coordinates, NGS coordinates. I have data sheets for them that have lat, longs, and heights that are all control quality. So if I wanted to on TMGO, I could fix all lat, long, and height on it. I do not have a control quality elevation on that point. So heights differ from elevations by the geoid model, unless I don't have the ability to put a control quality geoid model there. So the best quality coordinate I can calculate from an NGS data sheet for lat, long, and height is a survey quality elevation, and I can't fix that. So I have to have a control quality coordinate. So the next step in this process is for me to start fixing coordinates in my network that I want to tie to. I know that I want horizontal coordinates from PLTC and from TMGO. Even though they're tens of kilometers away from my project, they're the coordinates I want to base this project on. I'm assuming I don't have, for this survey and with this surveyor, I don't have any other control closer than that I want to use for horizontal control. Typically when I fix these coordinates or fix constraints, I do them one at a time and look at the results of each fix and continue to repeat that process until I have everything fixed that I want to finally fix in the adjustment. In this case, for brevity, to try to get this done in an hour, I'm going to fix 2 of these points and show you what happens. I'm going to adjust my network, and when I do that, the network adjustment is, I have enough degrees of freedom. I have enough observations in excess of the number of things I want to calculate in this network that it will calculate a set of transformation parameters for me from just putting those 2 points in. So if I look, all I've done at this point in time is essentially rotated the network and scaled all of my observations so that those 2 points uniquely fit those 2 control points, the coordinates that I tied down. So I'm going to look, and my reference factor hasn't changed at all, and I still pass chi-square. That's just indicating to me that it didn't distort my network at all. All it did was rotate it and make it and scale it and make it fit those 2 points. So if you look down here, I have 2 local constraints that were fixed for northing, easting, Latin, long, whichever you want to say. So I fixed those horizontal values. I have not fixed any vertical values, nor have I fixed any of these other points that are shown up in the control coordinate comparison section. So I have adjusted values for all of those coordinates now from this network adjustment based on the 2 horizontal constraints that I made. And
what are those question marks that you are looking there, Richard?
Yeah, okay, I'll get to that. Now, this table shows you the comparison between the adjusted values that I just calculated and any control quality coordinates you have for the points. Now for some of these points, again, for B412, the only control quality coordinate I have is an elevation. So it's telling me it doesn't know control values for northing, easting, so it's just showing you that it doesn't know those values with a question mark. In other cases, like PLTC and TMGO, I'm seeing question marks in that table because I fixed those values. So there's no difference between the adjustment and the control quality, control coordinate that I used. So there's 2 different reasons for question marks in the table. And this is a good time to kind of quickly glance around and see if there are any really significant problems with the existing control that you want to use to continue fixing for this network. And at this point, I'll just kind of leave it at that. And there aren't, I don't see anything standing out really badly. I'll get back to that though. And the other thing that's important to note is that as I constrain my network, I start to get transformation parameters calculated from the network adjustment. Now that's showing me a very small azimuth rotation and a very close to 1 scale factor for these because I have a very good fit between what the network's providing for me for differences in coordinates on those 2 points and the differences that actually exist if I inverse between them. So it's providing a little bit of rotation to the network and a little bit of scaling to make them perfectly fit over those 2 points. If I fix another horizontal coordinate in the network, I'm not going to get one set of parameters just like in an RTK calibration. I won't get one set of parameters that makes everything perfectly fit. What I'm going to have to do is start distorting my network a little bit, bending the vectors or moving them around to make it fit with all 3 points. So it'll do that in a way that provides the minimum amount of adjustment to my vectors in the network to make them fit with the points. Okay, so I'll continue on with my adjustment quickly and show you what happens when I start constraining vertically. Now in this network, my benchmarks are all down here in the final project area, down closer to my final coordinates that I'm looking to calculate. So I'm going to start picking benchmarks that make sense to try to constrain these for control for this network. So point S408 is a benchmark, and I'm going to fix that elevation. B412, the much touted point in our network that we talked about a lot, I'll fix that for elevation. Now if you look and draw a straight line between those 2 points, I'm actually calculating tilts to the whole network. So you can think of it as a tabletop. And I'm moving that tabletop around, tilting it in different directions to make the 3 vertical points that I'm going to fix right now fit perfectly, vertically. Okay, I also have rotated and scaled things to make everything fit horizontally, but I'm doing the vertical part right now. And you can see that I want to pick points that are far enough off, in a triangular shape the best I can around my network to get that tilt worked out the best so I get the best vertical final coordinate values I can on the final points. Now I have a benchmark here, 6.2, that I'm going to leave unfixed for right now, because it's basically on the straight line between energy and 412. Instead, I'm going to set this Jeffco reset elevation that I have from that benchmark as my 3rd point. So my triangle is a little bit better shape for trying to fix the vertical tilts for this particular set of unknown points. And when I do that adjustment, what you'll see in the adjustment report is that I really, again, haven't changed my statistics on the adjustment at all. All I did was rotate it, scale it, and now I've tilted it a little bit to try to fit my control perfectly. And that meets the minimum number of constraints necessary to calculate all of the transformation parameters that will be applied in the coordinate system definition after I accept this adjustment. So I have some tilts. You need to look at those and say, well, over the size of this project, do those kinds of tilts make sense? If you fixed one bad vertical right now, it would probably represent quite a large tilt in the network. I mean, if it was a really bad vertical value, and you would actually see tilts that don't make sense over the size of the project. If I'm seeing 30 seconds or 15 seconds even of tilt, that's an awful lot of tilt. So I'm looking at my different parameters. I'm looking at error estimates on those as well, by the way, on the right-hand side here, and trying to say, well, do these kind of make sense? Do I really have to tweak this network that much to make it fit? So that kind of gives you some feedback on how well your control, how good it looks compared to reality of the network.
So and Richard, would you ever, sorry to interrupt you, would you ever fix more than 3 points vertically? Jason is asking.
Yes, I definitely would. I'm just showing you the minimum number to calculate the transformation parameters. I would come back here and look at how well the rest of my fixes, if I have any additional ones, are compared to what I just got from that vertical adjustment. And if there's a very small number and it's not going to really distort the network to go ahead and fix more, I would fix every known control point I have typically. Sometimes that's excessive, but more often than not, you're starved for control. You're struggling to find enough control points to adjust your network. So you typically would wind up fixing everything that makes sense. Now in the United States, you can get national agency points mixed together with county points, mixed together with a city's control points, all of which have their own adjustments to them, and they may not fit perfectly well together. So if I'm trying to fit a national benchmark with a county benchmark with a city benchmark, that's all I have for control. I may find that they don't fit together very well. So in that case, you have to use your own judgment as a surveyor as to what you want to hold for your final control.
Yeah, question from Brooke is kind of in that direction. She's asking, is 2 points for horizontal and 3 points for the vertical the minimum, or they sometimes use only 1 point for horizontal?
So if you only use 1 point for horizontal because you don't have more, then that's the best you can do. You can't really work out if you need to rotate your network anymore. If you have more than 1 point, I would try to use it if you trust the control and how well the control fits together that you're tying to. And if I really want to say that my coordinates are relative to the NGS network, I pretty much have to fix more than 1 point in order to do that, because the NGS network itself has some adjustment in it, and it's basically defining its own local datum here, right? And I need to rotate into that datum and scale to really fit with the local datum before I can make a statement about my coordinates fitting that datum. So I would fix more than one if it's possible. You have to fix what you can.
So a question from Jay was on that vertical portion. Are you fixing the ellipsoid as opposed to the height? Or is that because you have a good ellipsoid model and you with the fixed height?
No, I was fixing elevations. And the reason is that I want to do a construction project in this area and water runs downhill. Ellipsoid heights don't necessarily represent what the gravity situation in the area and could provide actually water, basically a tilt in your vertical that do not indicate how water would run, for example. So I personally, for a lot of projects, would try to use elevations in the local area to make sure that everything is properly set up to match real construction kind of conditions and the gravity there. If you want to do a big control net and report ellipsoid heights in the end, then you would constrain ellipsoid heights. That's a little more rare, but sometimes if you're part of a big government agency, that may be what you finally report to customers and let them use the geoid to drive elevations. It's up to what you want to provide in the final coordinates for your project.
So in that case, you were fixing the elevation above the geoid, not the height above the ellipsoid, just to be clear.
That's correct. These are vertical benchmarks that have elevation values on them rather than the ellipsoid heights. I let the ellipsoid heights float for these 2 points, these distant points, even though I have control quality values for them, because they aren't likely to agree perfectly with the elevations that were derived from some other control net in my project area down here. And in fact, you can see that if you look at this report. Now that I've fixed the tilts for the local project, those points that are really, really far away horizontally, I have good GPS vectors to them, but I'm missing the delta heights that are taken from the geoid model and everything by pretty significant amounts. If you look at point hard, that has a good quality ellipsoid height, point PLTC and TMGO, these values don't look all that great for my match with the ellipsoid heights for those control points, but I don't care. I'm tying my vertical control here to my local elevations in the project area, and the tilts that are provided by that actually make those really far away points not match all that well. It's rare you're going to get ellipsoid heights over tens of kilometers that match with elevations possibly from a different agency in the project area. Okay? So getting pretty
Richard,
late.
As we are running out of time, I was going to ask you, can you show us just briefly the total station data and just mention some of the differences? Would you apply any different practices with total station or everything that you just talked to also applies to total station? Also, what happens if you have the mix of the two in the same project in that weighting strategy and things like that?
Yeah, so really quickly, if you look at the screen right now, what you're seeing are fairly circular-looking area ellipses for my final points. I really constrained geometrically, not perfectly, way out here on one side of my project horizontally, but I'm still seeing rather circular looking error ellipses. That's because GNSS vectors all have the same error source in this project. Now I have another project that has total station observations, and what you see is I have 3 different data types in this project just because of the nature of total station observations. And I get different reference factors for each one, and I have different error estimates for each one. Slope distances, vertical angles, and circular horizontal circle readings each have their own error estimate that you apply, and when you do the adjustment, they each one has its own reference factor generated for it that will scale each separate observation type separately, and you'll run the scalars for them separately. And because of that, when I go to calculate the final coordinates from my network, what you see is I have one control value fixed at the top of this network, but I have very different error estimates for my horizontal angles versus my distances here. And in fact, my distances are very tight in this network. So when I calculate the coordinate for this point right here, derived from that control quality value, the error ellipse that results is shows a very, very good tight distance measurement, but a broader or wider, relatively speaking, angular error that's calculated here. And this is not uncommon for error ellipses for total station data. And the farther I get from my control, the errors essentially add up the farther and farther I get from my control. So you see the size of the error ellipses grows. That's not uncommon either, and that occurs both for GNSS and for total station data, but the GNSS data all come from the same data source, so the final error ellipses just tend to be more circular because they're all correlated errors and essentially grow together or shrink together. So yes, you weight differently. You'll go and weight each section. So if I look at the weighting in this network, I have different scalars that I'm applying for each of the different observation types, and I'll do that scaling one at a time and look at the impact on the results and check my resulting adjustment each time, and I'll do them in order based upon this redundancy number you see on the right hand side. That's telling you basically how much that particular set of observations or that type of observation contributes to the overall network. So the greater the number for redundancy, the more impact that particular data type has on the overall network adjustment. So you would start with the most influential one first and try to get the error strategy or the error estimation right for that first by scaling. And then look at the remaining parts and continue to do the scaling until your network reference factor equals 1. And frankly, I like to try to drive these numbers pretty darn close to 1 if I can. Sometimes the numbers will be a little bit off of 1 and still pass the chi-square. And statistically, people say you don't really need to go any farther than that. I just makes me feel more comfortable to have all the weighting, relative weighting between different data types as close to 1 as possible. And if I had GNSS in here, you would see yet another set of statistics here for the GNSS stuff. And you weight those correctly as well, and drive the reference factor for the GNSS data close to 1 as well.
So,
okay.
Richard, the question for Mark was on a purely total station adjustment. Is it correct that you have to constrain the initial setup and azimuth for the initial unconstrained adjustment?
Good question. I think the answer would be you'd have to have at least one control point fixed horizontally and the some way to orient the network just for the comp engine to work. And if you try to do it without either a reference azimuth that you're using as a basis of bearing or a second control point that was used for the backsite, that it may not be able to actually calculate all the coordinates for the network. So you can play with that a little bit, but I'm pretty sure what he's saying is correct. You have to have basically the placement of the initial starting point and an orientation to get the network to calculate. That's a unique, still what I would call minimally constrained adjustment, as long as that's all you do. If you fix 2 points, you got a distance in there, and it actually is not as great as a distance and a coordinate, control coordinate and an azimuth, but it still works.
As you said, Richard, in that case, even the comp engine would not work, and you would not get those things displaying in your
Yeah,
plan view if you don't have those
that's right.
minimum
Probably
set
not.
of observations.
Yeah.
One thing I did want to highlight, one of the newer features in that, if you flip back to TBC, Richard,
Yeah.
is in that constraint window. If you move to the constraint tab, there is an ability to add azimuth constraints. So if you want to fix to a certain bearing, you can do that here easily by fixing an azimuth from point to point. Fixing two coordinates horizontally would have the same effect, in fact.
But it does also fix a distance in some respects too. So it makes it a little bit more. I like an azimuth to get. Oftentimes in the United States, you have to get onto a basis of bearings or some reference azimuth, and this is one way that you can do that for your adjustment to make sure that you're tied to the control the way that the agency wants you to be. Additionally, there's one last thing on these coordinates. I'm fixing those coordinates, so I'm basically saying that I have 0 values for how much I'm letting those coordinates float around. You do have the ability to apply constraints that are non-zero on your coordinates. Let them float around a little bit when you're mixing and matching control from different agencies. Sometimes that's necessary just to get it to work, but because that will allow you not to have to overly distort your network if you know roughly how well those control values fit together. Be careful using that. You need to do a bunch of adjustments before you get a good feel for how that works.
Excellent.
Okay, I think that I've pretty much covered the main topics for the talk, and I can go back and let Boris summarize for you.
So as you saw today, some of the best practices and workflows is summarized here. The first thing we've done is we've set our error estimates. We've paid close attention to that default standard errors that play a big role in our network adjustment. Then what Richard did next was doing an unconstrained adjustment first and working out the weighting strategy. So that pay attention in there to the reference factor, chi-squares, make those chi-squares pass. Once you do that, then you kind of focus on that helps you identify any blunders or issues you might have in your network, and then once you're good with that, you start adding constraints. You don't go back and you don't mess your weighting strategy anymore. You're set at that point. So then you start adding constraints at one at a time. So in the essence of time here, Richard kind of fixed multiple coordinates at the same time, but the good practice is to do one at a time and hit adjust. And every time you do that, make sure you review the report and you look at each constraint. We didn't go into the details. There's much more things in that network adjustment report, so you can look at the individual error ellipses and things like that. Certainly go through that report and pay attention to the more critical elements, and then once you're done, you can simply accept your adjustment. So for those that are new to TBC, so you can simply get started with tutorials. Everybody can download TBC. So having a license from installation is completely separate. So you can download TBC today. You can get a 30-day demo license from your Trimble distributor and leverage all the videos on YouTube that we have on this topic. Also, for our next Power Hour, we're going to be talking about machine control. So we're going to kind of be focusing on that round trip between GCS 900 and TBC, how to prepare CAD surfaces, site calibration for use with machine control data. So hope you can join us on that. And there was a lot of comments in the question box that this was a very interesting topic, and we might have actually a part 2 of this network adjustment. So kind of, Richard, I'm kind of putting you on a hook as well on that one, because this was a very this was very informative. Really appreciate you providing this extra value for our users, and thank you for being here with us today.
Okay, you're welcome. It's my pleasure. I hope that I helped you understand a little better how TBC is used to do this kind of work.
Excellent. Well, thanks everybody for attending. I hope we covered a lot of your questions throughout the session. If we missed your question or if you feel like you need more information, don't hesitate to reach to us on the email given to you when you registered for this webinar. And we look forward to hearing from you about additional topics you might be interested in. And thank you again for your time and attending, and have fun using TBC.
Thank you.
Thanks.